So let's go ahead and write an equation so we can kind of understand what's going on. So silver is silver plus, and carbonate is CO3 2 minus. So to write an empirical formula, we're going to write Ag2CO3. That's going to dissociate to 2 silver ions plus 1 carbonate ion. So if we want to think about what scene represents the solution at equilibrium with a solid, so again we're talking about taking a solid and kind of chunking it together with some water, or mixing it together with some water and asking how many ions are allowed to be in solution, we should see something that has a 2-to-1 ratio between the silver and the carbonate. So if we look at each of these molecular scenes and we ask what's the ratio of silver to carbonate, scene 1 is going to have 2 silvers for every 4 carbonates, so that's not right. Molecular scene 2 is going to have 3 for every 3. That 1-to-1 is not right. Molecular scene 3 is going to have 4 silvers for every 2 carbonates. That looks promising, and so looking at molecular scene 4, we've got 3 for every 4, and that's not correct. So molecular scene 3 best represents the solution at equilibrium, where we'd have a 2-to-1 ratio between the silver ions and the carbonate ions. So that one's pretty straightforward. Problem B says, in which, if any, other scenes will additional solid silver carbonate form? Okay, so what we have to do here is realize that molecular scene 3 told us we were at equilibrium. So from that, we can actually calculate the KSP. So KSP is equal to the concentration of silver squared times the concentration of carbonate. And remember, when we have molecular scenes, we're really just counting ions that we have in solution. So we've got 4 silver ions, and we're going to square that, 2 carbonate ions. And so the KSP for this is equal to 32. Now again, these numbers really don't make sense compared to the KSPs that we've been talking about in real problems, but in a molecular scene problem, all we're going to be doing is comparing Q, where we're at, versus K to see where we have the potential to shift. Okay, so we need to look at molecular scenes 1, 2, and 4, and we need to calculate Q. So for molecular scene 1, again, we're going to have the square of the silver times the carbonate. So we're going to have 2 squared times 4, and that's going to be equal to 16. Q is less than K, so we're on the left side of the equilibrium. We actually could have more ions that could go into solution with this case, so no precipitate. For molecular scene 2, Q is equal to 3 squared times 3 equals 27. We're still less than 32, so no precipitate. We won't be able to add as many ions to molecular scene 2 because we're closer to K than we were with the first one, but still we're below the maximum allowable amount, so there won't be any precipitate. Molecular scene 4, we've got 3 and then 4, so in this case, 36 is greater than the KSP. So in this case, we will form a precipitate. Okay? So we could also define these solutions as being what we call unsaturated. We don't have the maximum allowable amount of ions in solution, where this solution is saturated. It's actually beyond saturated, so we're going to have to take a few of those ions out of solution until we get to a point where our Q is equal to K, and then the rest of the ions can remain in solution. The last one here actually looks at thinking about how the addition of strong acid is going to affect this equilibrium. Remember when we had this sample problem before, we needed to ask about the potential of there to be any chemistry between this added reagent and the species that we have in solution. Well, we're never going to have 2 cations here react. So the question is there any chemistry that will happen between these 2 species? And the question is absolutely. This is the conjugate base of a fairly weak acid, and so this chemistry will happen. And when this chemistry happens, we pull this material out of solution. pulling a product out of an equilibrium will shift it to the right. So we're going to shift the equilibrium right, and that again is going to increase the solubility. Pretty straightforward, kind of applying some previous concepts from equilibrium that we've learned with our slightly soluble compounds to a really nice molecular scene problem.